Hi students, in this session we are going to discuss about some previous year questions related to dual nature of matter and derivative. In your mains preparation, modern physics, this is very important. The questions related to modern physics are very simple. Around 5 to 6 questions you have a chance, that is 24 marks easily you can get from the modern physics. And answering the questions related to modern physics are very easy compared to the remaining part of it. Basically, the questions from modern physics, they depends on 5 to 6 formula. Most of the questions are theoretical questions, conceptual based questions. So while answering the modern physics questions, you have to read the question thoroughly 2 to 3 times. This is very important while answering the questions related to the modern physics. But the questions related to this modern physics are very simple and you can score all 24 marks with a little concentration on that. Now in this session, I'm going to discuss about some important points you have to remember for GMAINS from dual nature of matter and radiation. As well, previous year questions related to this topic. Let us recap dual nature of matter and radiation. First, we discuss about the radiation. The main idea is radiation or light. It has the dual nature. In general, already we studied according to the quantum theory. The energy of light is given by N into h nu. This h nu is the energy of the photon and N is the number of photons and E is the energy of radiation. And energy, this is given by h nu or this is equal to hc by lambda, where h is Planck's constant, nu is the frequency, c is velocity of light, lambda is the wavelength. The value of h is 6.63 into 10 power minus 34 joule second. The value of c is 3 into 10 power 8 meters per second. Generally, the value of lambda is given in terms of meters, nanometers, micrometers, or angstroms. Already we know that nanometer means 10 power minus 9 meters. Micrometers means just 10 power minus 6, angstroms means 10 power minus 10 meters. To calculate the energy of photon, we use this to calculate the energy of the radiation. But a simple trick, already you know this. Simply remember, if the wavelength is given in angstroms, the energy related to this radiation is given by 12,400 divided by lambda. Your result is in electron volt. Suppose if you substitute joule second, meter per second, meters, your energy unit is joule. Substituting all these values, we get this. Again, whatever the result you are getting in joule, we are converting into electron volt. And to remember, 1 electron volt is 1.6 into 10 power minus 19 joule. This is very important unit for energy. Similarly, if energy is given in electron volt, the wavelength corresponding to this is given by 12,400 by E, and you get the wavelength in angstroms. And sometimes, based on these simple relations, also problems may be asked. I take one example. The wavelength of a light is 100 nanometers. What is the energy related to this photon? Yes, the wavelength is 100 nanometers. And in angstroms, it is 1000 angstroms. So energy related to this is 12,400 divided by 1000, and this simply you get 12.4 electron volt. Similarly, what is the wavelength related to a photon with energy 6.2 electron volt? The wavelength is, yes, 12,400 divided by 6.2. So what you will get? You get it is 2000 angstroms. Like this. This is one of the simple relation you have to remember. The next important topic related to this dual nature of matter is photo emission. Already you know what is the meaning of emission. In an atom, if the required energy is given to the electrons will be emitted. The energy will be given in terms of heat. If the electrons are emitted by heat, it is called thermal emission. If the electrons are emitted from a metal due to heat, if the electrons are emitted from a metal due to photons, that is due to light, then it is called photo emission. From certain metals, when light incident on these metals, if this light has more energy compared to work function of this material, then electrons will be emitted. In the incident of light, if electrons are emitted, this emission is called photo emission. And the metal which can emit the electrons due to incidence of light is called photometal. And the electrons are emitted. The electrons emitted are called photoelectrons. The condition is the energy, the incident energy of this light should be more compared to work function of this metal. The condition is incident energy of light should greater compared to work function of the metal. Now this work function is nothing but the minimum energy required to emit an electron from a photometal. In terms of photons, in terms of frequency, the incident energy is h nu. This should be greater compared to work function, and this work function is written as h nu naught. Here h is the Planck's constant and nu naught is called threshold frequency. The minimum frequency required to emit an electron from a photometal, h nu naught. When the incident frequency is more compared to threshold frequency, then only the electrons can be emitted. Sometimes the incident energy, if you write like this, hc by lambda, this should be greater compared to, instead of nu naught, I am writing hc by lambda naught. This lambda naught is called threshold wavelength. This lambda naught, threshold wavelength, this is the maximum wavelength up to which electrons are emitted. This is the minimum frequency above which electrons will be emitted. This is the maximum wavelength up to which the electrons will be emitted. The incident wavelength should be less compared to threshold wavelength, then only the electrons are emitted. For example, suppose if I take the threshold frequency of a photometal is 1 into 10 power 15 hertz. If the incident radiation is 1.5 into 10 power 15 hertz, yes, this is less compared to this, this is more compared to this, the electrons will be emitted. If the incident frequency is 0.5 into 10 power 15 hertz, the electrons will not be emitted. In terms of wavelength, suppose if I take The threshold wavelength of a photometal is 4000 angstroms, let us consider. If the incident wavelength is 3000 angstrom, then electrons will be emitted. That is, up to 4000, the electrons will be emitted. Suppose if incident wavelength is equal to 6000 angstrom, the electrons will not be emitted. Sometimes the simple idea related to this threshold frequency, threshold wavelength may give you the marks. In 2024 session, some questions are asked related to this. And the next thing, the experiment related to photo emission is very important. First of all, let us consider what is photo emission. Suppose if I take a photometal, when light incident on this metal, the electrons will be emitted. The condition is the work function should greater, the work function, the incident energy should greater compared to work function. H nu greater compared to H nu. For example, let us consider 5 electron volt energy incident on this. The work function is 3 electron volt. 3 electron volt is utilized to emit electron. Now, what happens to this 2 electron? According to law of conservation of energy, this energy is given to electrons in form of kinetic energy. That means simply I can write an equation H nu equal to work function plus the kinetic energy of emitted electrons. This equation is called photoelectric equation. And this equation is very important. Many questions will be asked related to this relation. And this equation is called Einstein photoelectric equation. H nu equal to H nu naught phi plus kinetic energy. This also can be written as H nu naught plus kinetic energy of electrons is half mv square. This also can be written as Hc by lambda equal to Hc by lambda naught plus the kinetic energy. And H nu equal to H nu naught plus the kinetic energy of electrons can also be written as EV naught, where E is the charge and V naught is the stopping potential. What is the meaning of the stopping potential? We discuss later. These are the different forms related to Einstein photoelectric equation. And this equation is verified with some experiments. Leonard, he done some experiment to verify this. The results of photoelectric experiment is very important. The graphs related to this experiment are very important. Now we discuss them. This is a simple experimental setup to study the photoelectric effect. And this is cathode, this is anode. The cathode is given high potential, negative potential. And anode is given positive potential. When you apply potential, and this is vacuum tube, we know that current will pass. But because there is some gap between these two, the current will not be conducted. When light incident on this, it is observed the current in the circuit. The circuit is not completed. When you apply the potential, you won't get the current. But when light incident, the current will appear. That means when light incident on it, the electrons will be emitted. These electrons are attracted by this anode. The circuit will complete. The current will appear. The current, it depends on the number of electrons collected. The number of electrons are more, the current collection is also more. The number of electrons are less, the current is also less. In this experiment, various factors are studied. The first one is the relation between intensity of radiation and current. The current is called photocurrent. The intensity of radiation and current. The intensity of radiation is taken on x-axis and photocurrent, this is taken on y-axis. Yes, with the intensity of radiation increases, the current is also increases. But it reaches to saturation. Why it reaches to saturation? This metal can emit some number of electrons. With increasing intensity, the number of electrons emitted will increase. But if the number of electrons emitted from the metal, it comes to saturation, the current also comes to saturation. This is one result. And in the same experiment, let us take a graph, kinetic energy of emitted electrons and frequency of incident radiation. The kinetic energy of emitted electrons is taken along y-axis. The frequency is taken along x-axis. Now this graph, you get a straight line, and this line cuts, this intercept is threshold frequency. And this graph follows the relation h nu equal to h nu naught plus the kinetic energy of emitted electrons, or k equal to, you can write h nu minus h nu naught. So the slope of this graph, if I take kinetic energy in this axis, the slope of this graph, this equation is in form of mx plus c. Yes. So the slope of the graph, it gives the value of Planck's constant. And this point is very important. The graph between kinetic energy of emitted electrons and the frequency will be like this. The slope of the graph gives the value of Planck's constant. Now, in same photoelectric, the graph between stopping potential and photocurrent. Now, what is the meaning of stopping potential? Stopping potential means the negative potential that should be applied on anode so that no electron can reach this. Generally, the electrons relieved from this have some kinetic energy. With this kinetic energy, these electrons can reach the anode. Suppose if I apply some potential here, the negative potential, at some potential, the electrons will be stopped. That potential is called stopping potential. That is EV naught. If I take EV naught, this EV naught is nothing but the kinetic energy of emitted electrons. That means this EV naught, this is equal to kinetic energy of emitted electrons. Now, if I take a graph taking stopping potential along y-axis and incident frequency along x-axis, then how you get the graph? Yes, exactly. This is also a straight line. And here it is u naught. Now, what will be the slope of this graph? For this graph, slope equal to? Yes. What will be the equation for this? EV naught, this is equal to h nu minus h nu naught, or V naught equal to H by E nu minus H by E nu naught. All these are constants. So the slope, this equation is similar to y equal to mh plus c. So what is the value of m? H by E. The slope of this graph gives the value of H by E. This is also important point. The slope of frequency stopping potential graph gives H by E value. The slope of frequency kinetic energy graph gives H value. Okay. Now, I take one more graph, the graph related to the photoelectric effect. I'm taking stopping potential along this is stopping potential or applied potential, let us consider, not stopping potential. Applied potential along the x-axis and the current along y-axis. Now, how you get the graph? Yes. At some potential, the current will increase and reaches to saturation. And if I extend this, here I get some negative potential. This potential is nothing but stopping potential. Suppose if I given 3 lines like this, this is related to, let us consider intensity of light, incident intensity. Of course, this is current. This is intensity. Let us consider the intensity of incident light is some E. This is E1, E2, E3. Now, in this graph, which relation is valid? Yes. Yeah, the current is more means this intensity is more compared to this. This intensity is more compared to this. That is E1 less compared to E2, less compared to E3. These graphs are very important. That is related to photoelectric effect. One thing you have to remember, Einstein photoelectric equation, and you practice how to do the problems related to Einstein photoelectric equation. And the second thing is graphs related to photoelectric experiment, that is Lennard's experiment. These two are very important. And another important and simple topic in this dual nature of matter and radiation is de Broglie hypothesis or de Broglie wavelength. And this de Broglie hypothesis or de Broglie wavelength, this is related to dual nature of matter. The hypothesis of de Broglie is matter in motion exhibit wave-like nature. The waves emitted from the matter waves. When matter waves are possible, it is possible matter in motion. And this matter, it should be quantum matter. And the wavelength, de Broglie wavelength is given by a formula h by p. H is the Planck's constant, p is the momentum. That is, this is equal to h by m into v. That is the momentum. The relations between lambda, mass, velocity, these are very important. Now, I take the different forms for de Broglie wavelength. The de Broglie wavelength, it is given by h by mv. This is one of the important formulas I have to remember. Suppose if I consider if a particle has kinetic energy, this is equal to k. Then we know that kinetic energy equal to p square by 2m, or this moment of p, this is equal to root of 2m k. Then de Broglie wavelength becomes lambda by root of 2m k. And related to these relations, last time question is asked like this. Electron, proton, alpha particle. These three have same kinetic energy. Then the relation between their de Broglie wavelengths. This is the question asked in 2020 for one of the students. To solve this question, we take this relation, lambda equal to h by root of 2mk. It is given the kinetic energy is same. So simply, wavelength is inversely proportional to mass. Now, according to masses, mass of electron is less compared to mass of proton. This is less compared to mass of alpha particle. So automatically it is inversely proportional. Wavelength of electron is greater compared to wavelength of proton. It is greater compared to wavelength of alpha particle. This is a simple question. Like these simple questions will be asked. Here K is the kinetic energy. And if I take electrons, if electrons are excited to a potential V, then what will be the de Broglie? When electrons are excited to a potential difference V, then the kinetic energy of electrons is E into V. So, the de Broglie wavelength related to these electrons is equal to h divided by root of 2mEV. This is the wavelength. And the problems related to this are also very important. Here h is the Planck's constant, m is mass of electron, e is charge of electron. If I substitute all these values, a simple technique, the wavelength related to electron excited to potential V is given by this formula. By substituting all these values, h value, m value, v value, you get. But this is in angstroms. For example, energy of electron is 5 electron volt. What is its de Broglie wavelength? The kinetic energy EV is given, mass h, the values you can substitute. And instead of going for this formula, simply you substitute lambda equal to root of 150. The electron energy is 5 electron volt, means it excited to a potential 5. So this is equal to, yes, root 30 angstroms is your answer. The same thing for proton, the same thing for alpha particle. Next another. For example, if I ask a question, what is de Broglie wavelength of electron in Bohr first orbit? Bohr first orbit. You know the atomic structure in Bohr first orbit that equal to n equal to 1. You asked it to find what is the de Broglie wavelength. Yes. According to Bohr postulate, the second postulate of Bohr is the angular momentum is quantized. Angular momentum is quantized. Have you remember this? This is the second postulate of Bohr theory. That is angular momentum, yes, L, this is equal to nh by 2 pi, here n equal to 1, or mvr, this is equal to nh by 2 pi, or mv equal to h by 2 pi r, the value of n equal to 1. Now, the de Broglie wavelength is h by mv. Now, h divided by h by 2 pi r. Now, this is equal to 2 pi r, where r is the radius of this orbit. Now, this is equal to circumference of orbit. These type of questions are also asked. Maximum questions related to the relation between lambda, mass, energy. I take one more question related to this, which is asked in previous year. An alpha particle and proton have same momentum. What is the ratio of their de Broglie wavelengths? Yes, the ratio of de Broglie wavelengths. We know the de Broglie wavelength is h by p. P is same. So lambda equal to p is constant means lambda is also constant. Yes, the de Broglie wavelength of alpha particle and proton. This is 1:1. Suppose in the same problem, that is alpha particle and proton have same de Broglie wavelengths. This is also asked. Now, what is the ratio of their kinetic energies? De Broglie wavelength equal to h by root of 2mk. De Broglie wavelength is same, that is lambda is constant. So you can write 2mk, this is equal to constant. Yes. Then what we can write? m1 by m2, this is equal to k2 by k1. We ask it to find what is the ratio of their kinetic energies. That is, I want k1 by k2. One is alpha particle, another is proton. The first one is alpha particle. Second one is the proton. If I consider proton mass is m, alpha particle mass is 4m. So you get 1:4. Students, very important thing. When the questions are asked related to these ratios, sometimes you may ask, what will be the ratio between de Broglie wavelength of alpha particle and proton? Sometimes you may ask, what is the ratio between de Broglie wavelength of proton and alpha particle? You observe, both options will be there in options MCQ. So, while answering the questions related to these ratios, study the question 1 to 3 times. Be careful about answering. These are some important points. This gives a recap to the dual nature of matter and radiation. These are some important points. And some questions I discussed. And in next session, I'm going to discuss more questions related to this topic which are given in previous years. Okay? Yeah, we wait for next session.